Here are a few more of these equilibrium problems here, and for this next problem we have a 5-meter long uniform plank that has a mass of 15 kilograms. So this plank right here has a length of 5 meters and the mass is 15 kilograms. And there are two supports as shown in the diagram. So here's the first support and here's the second support. And we want to find the force on the left-hand support here. So I'm assuming that we got to find the force acting on this support stand right there. Okay, so what we're going to do in order to kind of set this problem here is we're going to draw a free body diagram. So since the plank has a mass of 15 kilograms, we want to find the center of gravity, which is maybe approximately right here, and we'll draw a force acting in the downwards direction. So that's my force of gravity. And the two supports, they also have forces probably going in the upwards direction, and this will keep the plank in equilibrium here. So this is the force on the left-hand side, and this is the force on the right-hand side. Okay, so because there's distances in this diagram, we probably need to set up a rotational equilibrium concept here. And when we're doing that, we do need to find a pivot point. And for all the previous examples I've done so far, it's been recommended that you pick the pivot point on the far end here. But in this case, that may not help us. So a good skill that we're going to need to work on for this problem is picking additional pivot points so that we can set up this problem for success. So another good strategy that you could use for your pivot point is just pick the opposite side here. All right, so if this is your pivot point, what happens now is you can actually eliminate the force acting on that location, and now you just have a left-hand force and a force of gravity, and those forces are now being referenced towards the red pivot point. Okay, so if I'm referencing all my forces to the red pivot point, then this downwards force of gravity is now going in the counterclockwise direction for its torque. And this force on the left-hand side, this is going in the clockwise direction for its torque. Okay, so I'll call this kind of like your first torque, and this will be your second torque. So they're going in the opposite directions there. Okay, so let's go ahead and set up a rotational equilibrium concept here. So the sum of the torques equals to 0. And since there's only two torques in this problem, you're going to have a torque on one side and a torque on the other side to keep this in rotational equilibrium. The general formula for a torque is force times the distance, and force times the distance. And this force right here is corresponding to that force right there, which is the force of gravity times the the mass times the the mass times the acceleration due to gravity, mg. So that has to do with the uniform plank there. So the plank has a mass of 15 kilograms, and we're going to times that by 9.80. Now we need to find the distance with respect to the pivot point, right? So if I go back to my diagram here, we know this entire length right here is 5 meters, right? And the center of gravity is always halfway, right? So that green distance is going to be at 2.5 meters to the red pivot point. So this is going to be 2.5. And this force over here, this is the force on the left-hand side. And we also need to find the full distance to the pivot point. And it looks like, okay, let's just go ahead and break this down here. It looks like the left force is actually 3 meters away from the pivot point. Okay, so we will go ahead and just put in the number 3 here. And now we have enough information to find FL, which is the force on the left-hand side. I'm just going to pause the video here, and you can go ahead and calculate what FL will be, and I will unpause the video with the answer shortly. And the force on the left-hand support stand is 122.5 newtons, and if you want to round that down to two significant figures, that's about 120 newtons there. Okay, so that's the answer for this particular problem. Here's another good equilibrium problem where we have a few things going on. So we have an 80 kilogram 12-meter uniform diving board. So this whole diving board right here is 12 meters and its mass is 80 kilograms. And it's in static equilibrium. So static equilibrium is another way of saying that the the sum of the torques is equal to 0, and the sum of the forces are also equal to 0. So we're just combining both rotational and translational equilibrium for this problem. Now there's a little twist here. It says that support A is providing a force of 3,000 newtons in the downwards direction there. So if I look at support A, there's actually a force going in the downwards direction. I'll call that F. And this is actually equal to 3,000 newtons. Okay, and we want to find the force provided by support B and the distance L. Okay, so there's a lot going on here, so let's go ahead and draw a free body diagram. So this diver has a force of gravity acting on it. I'll call this FG2, and that's because the diving board has a center of gravity, and I'll put a force going in the downwards direction. I'll call this FG1. So those are all the forces acting in the downwards direction. So we have 3 forces acting in the downwards direction. So what that means is force B should have a force going in the upwards direction, and that will ensure that, I'll call this force B there, that will ensure that this diving board here is in static equilibrium, it's not moving. So all the forces need to be balanced. I can't have another force going in the downwards direction because that would mean that the diving board would not hold. So at B, the force should be going up. So a little bit of a twist for this particular question here. Okay, so what we're going to do here now is we got to kind of think about how to kind of break up this little problem here. Since I can calculate 3 out of the 4 forces, I will start off with the translational equilibrium concept. So I'm going to rewrite that down here. So sum of the forces equals to 0, and that's because I know this force in the downwards direction, I know this force in the downwards direction, I know that force in the downwards direction, therefore I can find this force in the upwards direction. Okay, so what that really means here is sum of the forces in the upwards direction should equal to the forces in the downwards direction. Okay, so in the upwards direction, I just have the force at support B. And in the downwards direction, I have the 3,000 Newton force that was given to me at support A. And I also have FG1 and FG2. Okay, so what is FG1 and FG2? Well, that's just the mass times the acceleration due to gravity, right? So if I erase this now, FG1 is the mass of the board. So the board has a mass of, the swimming board has a mass of 80 kilograms, so I times that by 9.80. And the diver has a mass of 70 kilograms, and I times that by 9.80. All right, so this is really your FG1, and this is really your FG2. All right, so now we have enough information here to find the force at support B here. Okay, so this is going to be a 3,000 plus 80 times 9.80, so that's going to be a 784. And then we have 70 times 9.80, that's going to be 686. And force B now, if I add up all these numbers here, we should get a force of 4,470 newtons. All right, so that's the force acting at support B. Okay, so I'm just going to erase all this here because we're done with the translational equilibrium concept. And let me just erase that. Okay, so force B, we just found out that that is 4,470 newtons. Okay, so now we're done. So now we're done with translational equilibrium. Now we want to attack this problem using the sum of the torques being equal to 0. So that right there is rotational equilibrium. Okay, so now we need to find a pivot point because our goal here is that we need to find this distance L now. Okay, so yeah, you want to find a very good pivot point here. So you do have a few options here. So, you know, I'll put my pivot point at the very end here. And if I put my pivot point at the very end, I can eliminate this force over here. And since I'm referencing everything with respect to the red pivot point, FG1 is going in the clockwise direction, FG2 is going in the clockwise direction, and the force at B, this is actually going in the counterclockwise direction, right? All right, so it's very important that you're aware of the direction of the torques there. So let's go ahead and set up our torque expression here. So sum of the torques at the pivot is equal to 0. So we have a torque 1, so I'll call this torque 1, and this is torque 2. Those two torques are going in the clockwise direction, and in the counterclockwise direction, that's going to be torque 3. Okay, the general formula for torque is force times the distance. Now, there's no angles in this particular question, so that's good. So let's take a look at this force right here. So that's going to correspond to that force right there. So that's going to be mass times the acceleration due to gravity. So this this diving board has a mass of 80 kilograms. The acceleration due to gravity is 9.80. And then we got to figure out the distance, right? The distance to that red pivot point. So if I look at this distance right here, so the diving board is the center of gravity. So if the entire length here is 12 meters, if the diving board is 12 meters, then half of that is going to be 6 meters. Okay, so I'll put 6 meters right here for the diving board. Actually, let me just give a little more space here. So 80 kilograms for the diving board, and it is 6 meters away from the pivot. Now the swimmer has a mass of 70 kilograms, and we times that by 9.80. And the swimmer is actually a full 12 meters, the full length of the diving board away from the pivot point. And then finally we have a force over here, which is force B. Now we just calculated force B to be this number right here, 4,470. So this is 4,470. And this distance we don't know, so we will now calculate the distance D. So let me just erase all this. So what we need to find is this particular distance right here, the distance D there. Once we know that distance, then we can go backwards and find this length right here. So that's not a problem at all. Okay, so let's go ahead and find this particular distance right there highlighted there. And this is another linear equation here. So I will pause the video and then I will show the video in just a, I'll show the answer in just a sec here. Okay, so the distance that I've calculated here is 2.894 meters. So that's the distance from force B to the pivot point. So if I go back to the original diagram now, let's go ahead and erase a lot of this. Let me just erase all these colors here. So what we just kind of figured out here was this particular distance right here was the 2.894. And therefore we can find this distance here by taking 12 meters and subtracting that answer. And if we do that, we should get 9.106 meters. All right, so that's the distance of length L right there. So another good static equilibrium problem here. Here's another good thinking equilibrium problem. So we have a uniform 0.122 kilogram rod that's 0.9 meters of length. So this whole rod right here has a mass of 0.122 kilograms, and the length here is going to be 0.90 meters. And it's used to suspend two masses as shown below, and we want to find what distance x should the 0.2 kilogram mass be placed to achieve static equilibrium. Okay, so static equilibrium is just another concept of saying that the sum of the torques is equal to 0 and the sum of the forces are equal to 0. And it still just means that the overall diagram is not moving. Okay, so a very good thinking problem here, and I'm going to approach this question by using torques. And let's go ahead and draw a free body diagram here. So I'll call this FG2. I'll call this FG3. And since this uniform rod right here has a mass of 0.122 kilograms, it has a center of gravity. So I'm going to put that somewhere over here, and I'll call this just FG1. Okay, so those are all the forces in the downwards direction, and the support also provides a force, and the force it has to go in the upwards direction because we have too many forces in the downwards direction, so we must have at least one force to kind of offset all the vertical downward forces there. So the support of the stand is highlighted there in red. So there's my free body diagram. Okay, so the other thing I want to do now here is, because I want to tackle this question using the concept of a torque, I want to use a rotational equilibrium. So sum of the torques equals to 0. And I need to find a good pivot point. And I recommend putting the pivot point over here at the support stand. And if I put the pivot point at the support stand, then I pretty much eliminate this force there. Okay, so the next thing you have to do here is, if that purple dot is your pivot point, you need to figure out how the torques are moving. So FG3, this is kind of going in the clockwise direction, right? Because that's being referenced to the purple pivot point. And that would mean that FG1 and FG2, those are going in the counterclockwise direction. Okay, so you want to be able to know what direction the torques are moving, and that happens after you pick your pivot point. So if you're in the clockwise direction, I just have the one torque here, so I'll call this torque 3. And in the counterclockwise direction, I have torque 1 and torque 2. Okay, so this is going to be that torque, and that's going to be that torque over there. Okay, so the general formula for a torque is force times the distance. And the general formula for torque is force times the distance plus the force times the distance here. Okay, so let's go ahead and work on torque number 3 here, because we know the mass here is 0.50 kilograms, and the distance from the pivot point is going to be 0.25 meters. So if I go over here, the force here is mass times the acceleration due to gravity. So for torque 3, it's going to be 0.5 times 9.80. And as I mentioned, the distance from the purple pivot point is 0.25 meters. All right, so that takes care of all the torques in the clockwise direction. Okay, for torque number 1 here, the force of gravity. Well, here's torque number 1. So the mass is 0.122 kilograms. So I will write this as 0.122 kilograms, and we times that by 9.80. And then we're going to find the corresponding distance from the purple pivot point. And this takes a little bit of work. So let's go back to our diagram now, and let's figure out how to find the distance to the pivot point. I'll erase this now. Okay, so we need to find this green distance, right? That's the distance to the pivot point. Okay, well, we do know that the center of gravity is half the length, right? So the full length, as mentioned, was 0.9 meters, right? So if I get out a red marker here, this full length is 0.90 meters. So the halfway distance there is going to be 0.45. So now we need to take in consideration this distance right here, this yellow distance, which is 0.25, and we know that this blue length right here is 0.45. Okay, so if I take blue minus yellow, so 0.45 minus 0.25, then this distance here should be 0.2, right? So 0.2 plus 0.25 should give you 0.45. Okay, so this distance here is going to be 0.20. Okay, and finally we have, let's put a plus sign there, and we have another force over here. That's going to be this torque right here. So that has a mass of 0.2 kilograms. So the mass is 0.20 kilograms times by 9.80. And we need to find the distance x, right? All right, so we've now set up our rotational equilibrium concept there, and our goal now is to find this variable x, and this is just a linear equation now. So I'm going to pause the video, and when I unpause, I will show you the answer that I have calculated. And the final answer that I've calculated is 0.503 meters. All right, so that's the distance x that we've calculated for this particular problem. And just to kind of finish off, let me just go back to our diagram here. So I always need to erase some of the colors here. And this distance right here in green, this has the value of 0.503 meters. Alright, so that concludes this video guide on static equilibrium problems, and most of the problems that we covered in this video, a good skill to kind of work on is being flexible with finding where to place that pivot point, and once again using the rotational and translational equilibrium concepts.